synapses. What is the difference? Apart from changes in membrane potential, obviously one is hyperpolarizing and another one is depolarizing. But why is that? Because different channels open by different mediators. So we have excitatory mediators, which bind to their receptors, which form part of an ion channel. And that channel will open. Examples: acetylcholine. It binds, actually 2 molecules of acetylcholine are required for excitation of one receptor. They bind, and the channel is open. The channel is poorly selective to cations, but it is selective against anions. So chloride will not go anywhere, but cations may go. That gives you depolarization. How about inhibitory? Examples of inhibitory mediators: GABA, gamma-aminobutyric acid, glycine. And that's about it. Now, you seem to remember bits and pieces. Now let me make you think about creative use of that. The question is this: when you open cation selective channels, our membrane potential goes towards depolarization. Why? Because we have negative membrane potential inside, and cations, most of them, except for potassium, have positive reversal potentials. So that's what drives cations towards the reversal potential. So depolarization is understood. Why we have hyperpolarization? Because we have little chloride inside, more outside, and when we open channels for chloride, even at negative membrane potential, the concentration gradient for chloride ions is such that chloride will enter into the cell. But remember, chloride is charged negatively, so it will bring more negative charges into the membrane, into the cell. That will provide hyperpolarization. So my question is this: can we convert somehow excitatory synapse into inhibitory synapse? i.e., stimulation, you do something to the nerve, to the neuron, whatever you like, and then you stimulate excitatory fiber. Acetylcholine is released, but instead of depolarization, you see hyperpolarization. What do you need to do? You need to set membrane potential close to reversal potential of your ions, close to 0 or above 0. So in that case, you open gates for cations, for potassium, but it will now want to go out, not in sodium, calcium. This doesn't happen with cations, simply because one of the reversal potentials, sodium in sodium, is very positive, plus 61. No normal cell can tolerate resting potential plus 61. It can reach that during a peak of action potential, but that is very short. So that's not a realistic situation, and it doesn't happen. However, the situation with inhibitory synapses is different, because we have negative potential already here, and chloride is entering only driven by its concentration gradient, despite the negativity. It's easy to make it go out even from low concentration to high concentration area simply by hyperpolarizing the membrane. So if you stimulate inhibitory inputs into a neuron, it will hyperpolarize more and more towards chloride reversal potential, and then you start stimulating more inhibitory inputs. Will there be more hyperpolarization? No, because there is no driving force. You're already at the end of the road, so to speak. So inhibitory potentials critically depend on the prehistory, on current value of membrane potential. If it hyperpolarized, there will be less contribution of inhibitory, but more contribution of excitatory, because stronger driving force for cations to enter. So that's the logic by which neurons process incoming information. It depends on the state of the neuron, namely membrane potential, current value. When we say -70, it's not something set in stone, it's variable. In the majority of neurons you will find it, but some of them will be at -90 and not reacting to inhibitory potentials. Some will be at -40 and reacting to inhibitory potentials much easier. Okay, so that's basically how you apply that knowledge. Now, how mediator is released. This is something that was difficult in previous years. The mechanism. Slide. Yeah, here. So you need to remember this sequence. What happens at the presynaptic terminal? This is presynaptic neuron, and this is postsynaptic, which you want to drive, to tell, shut down or excite. This is our neuron at the bottom, and these are inputs. So everything starts with action potential arriving to the presynaptic terminal, and that brief depolarization due to sodium current opens another class of calcium channels. You will hear about them a lot in the next few lectures, voltage-gated calcium channels. These open in response to depolarization, similar to sodium channels. They close because of voltage-dependent inactivation. In a similar manner, there is an activation gate, not in all classes of calcium channels, but in this one, yes. This one is called N-type calcium channel, neuronal, and it can inactivate. Some others don't inactivate, or practically inactivate so slowly, so during the time of an action potential there is no measurable inactivation. These are L-type calcium channels. L stands for long-lasting, and they are present in cardiac muscle and in smooth muscle, and we will come to them in due course. But in any case, the process here is very rapid, short action potential, short injection of calcium through voltage-gated channels, jump in calcium concentration. Calcium goes up and diffuses and interacts with proteins, docking the vesicle full of mediator and making that vesicle fuse with the synaptic membrane. So the result of that, the content of this vesicle now has a passageway out into synaptic cleft. So that's the process triggered by the rise in calcium. How do we know that? First, these channels were measured using electrophysiology technique, Planck. Secondly, we can fill this presynaptic neuron with a compound called caged calcium compound. It's a tightly binding calcium molecule called cage, and it's indeed like a bird in a cage, closed cage. So calcium wouldn't dissociate. You have a lot of it, but it's bound. It wouldn't do anything to mediate the release. Okay? Now, the beautiful feature of that caged molecule is that if you irradiate it, illuminate it with UV light, it breaks. And whatever calcium was bound is released now. And that's the way of rise calcium very rapidly without opening any channels here. It just flash light. So these experiments were done in late 80s, early 90s. And what happens when you flood this with calcium from inside? Excitation postsynaptic potential. So that proves that you have calcium mediated mechanism. Likewise, there are opposite to caged compounds molecule called calcium scavengers. They have low affinity to calcium, but you can load them into synaptic terminals here. So you don't touch calcium, whatever calcium is there. But if you irradiate that molecule, it becomes hungry for calcium and binds calcium very rapidly. So if you do that, just before you stimulate action potential, there is no postsynaptic potential. Why? Because whatever calcium came in is bound, and there is no effect of calcium. So these two facts have proven a calcium hypothesis. So what you need to remember is that calcium plays a pivotal role in synaptic transmission. Now, what will happen in hypocalcemia? If we, for whatever reason, don't receive enough calcium, and calcium from our bones is not released, so we have low abnormal concentration of calcium in the blood. The first effect would be impact on synaptic transmission. So the first symptoms would be neurological symptoms connected to improper transmission of excitation across synapses. Likewise, if you have excessive calcium, there might be accentuated transmission with all the consequences. But increased calcium is also dangerous in terms of overloading smooth muscle cell, vascular smooth muscle, rising blood pressure, and cardiac muscle producing stronger contractions and contributing even more to raised blood pressure. And that's why calcium is tightly regulated in our bodies, and we have very constant level of 2.8 millimolar calcium outside. Okay, any more questions? Resting potential, action potential, propagation, all this is understood? Or isn't? No? Okay. So how about resting potential changes in response to high potassium outside? You did your simulation experiment and you increased extracellular potassium very little, from 4, which is normal, to 6. What will happen to membrane potential if you increase it not to 6 but to 60 millimolar? Of course, no animal will survive that, so you have to isolate cells and play with them in vitro. Now, the question remains, what will happen to membrane potential? Depolarization or hyperpolarization? Hyper. Okay, why? You have a lot of potassium inside, little outside, and potassium leaves from the cell, exits, leaving negative charges behind. That's how membrane potential, resting potential is formed. Now you upset that non-equilibrium. You increase it outside. What will happen to membrane potential? It's not inside, it's outside. So that will decrease resting potential from -70 to -30 or 0 or whatever. For -60, it will be something like -15 millivolts. It's huge depolarization. What will happen if you remove potassium altogether? What will happen to membrane potential? Theoretically, it should be hyperpolarization because of stronger gradient. There were 4 outside, now 0. So whatever was inside can come outside with lesser effort. There is a driving force which is stronger. That's what one would expect if membrane was behaving like Nernst said it will behave, i.e. selectively permeable to potassium and nothing else, if there was no anything else. In reality, we have calcium channels, we have sodium channels, we have chloride channels, which are, some of them are sensitive to concentration of potassium outside. So when you remove gradient to investigate the role of that gradient, you're also impacting on these potassium sensitive channels. But most importantly, remember I told you about active transport, sodium, potassium, ATPase, which grabs free sodium from inside, throws it out to potassium inside. So the balance is one positive charge in cell, it hydropolarizes. It turns out that this pump is not only transporting potassium from outside to inside, but is also activated by potassium. So if your concentration of potassium is 2 millimolar, and then you increase it to 2.5, 3, that makes pump work stronger. Not because there is more to transport, but because potassium, in this case, acts as activator. Like adrenaline for the heart, but it's much simpler, just an ion. So that's the effect on potassium pump, sodium potassium pump, which is present. So theoretically, you should see hyperpolarization. In practice, that hyperpolarization is either much bigger or smaller, depending how much potassium you add or decrease. Because this sensitivity to potassium is pretty steep and with very narrow concentration gradient between 0.5 millimolar and about 6, 7 millimolar. So within this range, you will have two effects, very similar. One will be, say, you are increasing slightly, like we did in our experiment. That will impact on depolarization, increase excitability, but it will also activate sodium-potassium ATPase, and it will create effect on red potential. If you decrease it to 0, sodium-potassium ATPase will stop working, and remember, it was contributing to hyperpolarization. Now you stop it. So there will be depolarization instead of hyperpolarization. But these intricacies will come into play later in future years when you will need to understand arrhythmias in the myocardium in a couple of years' time. But these are important for pathogenesis of some of the most dangerous conditions in cardiovascular medicine, cardiac arrhythmias, and I will tell you more about it in more detail in due course. For now, just make yourself familiar with the basics. Okay? More questions? Let's take registration. I think you are supposed to register for revision as well as normal lecture. Yeah. Get your phones out and take registration. Done? So we started with very basic